So in this video, we're going to take a look at the limit comparison test. So a lot of students think that the comparison test that we looked at in the last video, sometimes referred to as the direct comparison test, is a little confusing. And it is, because you have to pick a comparison series. You have to know if it converges or diverges, but that's not a problem. But then you have to know whether that comparison series is always greater than or always less than the original series. And then if one converges, the other one diverges, or blah, blah, blah. So that gets a little confusing. So the limit comparison test for many students is a little more straightforward, I think. It involves taking limits. All right. So once again, we're going to be selecting a comparison series. And just like with the direct comparison test, B sub n will be our comparison test. Okay, this is the one we're using as our comparison series. And A sub n will be the original series, just like we did in the direct comparison test, or otherwise just known as the comparison test. And the most important part of this is really the first part right here. And so what we're doing is right here, it says, if we take the limit of A sub n divided by B sub n, so we're taking the limit of a ratio of A sub n divided by B sub n. If the limit exists, in other words, if the limit is equal to L and L is not equal to 0, then both series converge or both series diverge, right? That's where most of these problems are going to fall into. Now, if the limit of the ratio is equal to 0, or if it's equal to infinity, generally speaking, it's going to be inconclusive. But you also want to just go back and check with these two situations. So let's dive in and do the first example. So here is our A sub n, 1 over the square root of n plus 1. And so I'm going to compare that to 1 over the square root of n, which could be rewritten as 1 over n to the 1/2, which is a diverging p-series. Diverging p-series. So that's the first step, just like with the direct comparison test. Select a comparison series that you know that it converges or diverges. Now we are taking the limit of the ratio. And so A sub n is always on top and B sub n is on the bottom. And so this is a complex fraction, of course, so we multiply by the reciprocal. And then we can simplify it to this, and then you can find the derivative of that either by L'Hopital's rule or dividing the numerator and denominator by the highest power of n, which is what I did in this particular case, which is a technique we learned for limits a long time ago. And so when you do that, you end up with the limit of 1 over 1 plus 1 over the square root of n. And when you take the limit as n approaches infinity, you end up with 1. So 1 is equal to L, which is not equal to 0, and therefore the limit exists, and therefore the conclusion is either both series diverge or both series converge. And since we know that we have a diverging p-series, that means that our original series here that we are concerned with diverges. I added another one in here because I had all this room. I hated to waste the room. So I just stuck another little problem in here. Let's do that in purple. So here is my series, A sub n, 4 divided by the square root of n squared plus 5. And so I'm going to compare, so it says because the square root of n squared simplifies to n, choose 1 over n as the comparison series. So you have to be kind of algebraically creative with these problems. So looking at the denominator, you have the square root of n squared plus 5. Well, we know we're going to be taking the limit of this. And as we take the limit as n approaches infinity, the 5 really becomes meaningless. All right, infinity plus 5 is still infinity. So really the denominator, the important part is just the highest powered term. Which is the n squared. So the square root of n squared is equal to n. So really in the denominator, what we have is n. And so that's why I chose 1 over n as my comparison series. And so we know that 1 over n is a diverging harmonic. All right, so taking the limit of the ratio of a sub n divided by b sub n, and of course I'm skipping that step and going right to multiplying by the reciprocal. And so we end up with this. And so when you take the derivative of the numerator and denominator using L'Hopital's rule, or you divide the numerator and denominator by the highest power of n, which incidentally is n, any way you want to take the limit, you're going to end up with 4, which is not equal to 0. And so therefore, both series converge or both series diverge. And once again, we know that 1 over n is a diverging harmonic. So therefore, both series diverge. That's your bonus question in there. All right, the next one. Some of these get a little trickier. What should we compare this to? Well, again, in the numerator, the 1 is really inconsequential. And this is a lot like when you learned about finding limits of rational functions. When you find the limit of a rational function where you have a polynomial in the numerator and a polynomial in the denominator, the only terms that are really important are the leading terms, the highest powered terms. So it's really the same thing here. This is a rational function, 2 to the n plus 1 over 3 to the n. Essentially, it's just that 2 to the n, 3 to the n are not polynomials. So the 1 in the numerator becomes inconsequential. So really, the important part is we have 2 to the n over 3 to the n. And so that's what I'm going to compare it to. I am going to compare 2 to the n over 3 to the n, which can be rewritten. 2 to the n over 3 to the n can be rewritten as 2/3 to the n, which of course is a geometric. All right? It is a converging geometric because r, absolute value of r, is 2/3, which is less than or equal to 1. Okay, so that converges. It's a converging geometric series. So we know that. That's our comparison series. So then it's just taking the limit. So all of this is just taking a limit, and the limit ends up being equal to 1. And so when you're going from here to here, the 3 to the n's cross cancel here. And so it's just a little bit of algebra. And then here, dividing the numerator, each term in the numerator by the denominator, you end up with this. And then clearly, you are going to end up with 1, which is not equal to 0. And therefore, both series converge or both series diverge. And since we know we have a converging geometric, then our given series, a sub n, will converge. And let's see, and the last one, yep. And another one with the log function. We always love the log function problems. And so we're going to compare this to 1 over n squared. Sometimes you just have to guess. I hate to say that, but sometimes you just have to guess. We had another log problem once where we compared it to 1 over n, and that worked. That would not work here. If you take 1 over n squared, actually, you could try taking well, in this problem, it's inconclusive. So if you're comparing it to 1 over n squared, which we know is a converging p-series, and so we take the limit is infinity. All right, so if the limit is infinity, that generally means it's going to be inconclusive. But we could go back, and we could go back to here and say, okay, what happens if the limit is infinity, like it is here? Okay, well, if the limit is equal to infinity, then if b sub n diverges, a sub n diverges. The problem is, in our problem, b sub n converges. So therefore, it's inconclusive. If b sub n converged, then a sub n converged, but that would only be true if the limit of the ratio was 0. Since the limit of the ratio of a sub n, b sub n is infinity, and because b sub n converges, not diverges, we get nothing out of this test. So there's a couple of things that you can do. Sometimes you can try using a different comparison series. If you use a different comparison series, like I wrote down here, by choosing 1 over n to the 3 halves as the compare series, it can be shown that both series converge. However, it will be better to use a different convergence test, right? Because what can get confusing with these is people will say, why did you choose that particular comparison series? How do you know that it's really a good comparison? And sometimes you just guess, and sometimes it's not. You want to try to keep your comparison series looking as similar to your series in some way as possible. Now, what is the relationship between A sub n right here and this? I don't know. They don't look anything alike. So we could see if we use this, go ahead and try it. If you use 1 over 3 halves power, which is a converging p-series test, then the limit will end up being existing, and therefore the convergence the limit convergence comparison test will say that it converges. However, you are going to learn other more useful types of tests to do in this case, so that you don't have to be trying comparison series after comparison series, because they can get a little bit confusing. But if you want to, I urge you to try doing this. You've got some space down here that you can do it in, and see what happens with that. All right, so that is the limit comparison test, and we looked at the direct comparison test, and it looks like we're just going to have 2 videos. I might, if I have time, post a bonus video where I just do a few more examples of both of these. All right,